In this video, we're going to take a look at one slight wrinkle with these volumes of solids of revolution. So we're going to take the line y equals x to the 1/2, which hopefully recognizes the square root of x. So we should know what that looks like. It'll go through 1, 1, 4, 2, 9, 3. But this time, instead of rotating it around the x-axis, we're going to rotate it about the line y equals 3. So actually, there's some words missing here. Sorry, I'm not sure why that was cut off. But the first quadrant area between x equals 0 and x equals 9, underneath the curve, y equals x to the 1/2. So we're talking about the area down here. Is rotated around. So this is the area that's going to be rotated around that green dotted line. What's slightly different about this is, maybe you can imagine it when you're seeing it, but if you take this area, and we'll just pick a random spot on here. We'll start with when x is 4. If you imagine rotating this around the line y equals 3, well, this point will be rotated in a circle around here. And this will be rotated all the way around here. But what's going to be happening is it's this part out here. You can sort of see the outer ring of the circle is going to be the solid object. The inner ring is not. We'll see what happens if I'll rotate this around. And then when we rotate this around, and then every other point in the middle, it's going to be the same thing. What's going to happen is this is going to form almost like it's like a tin can, like a cylinder, like we had, similar to what we had in the last case. But in this case, there's going to be a hole running through the middle. And so what we do when we find the volume here is we have to realize that the volume is going to have of the object that has a hole in it can be calculated by taking the object of the whole solid object and subtracting the hole. Now, what we're going to do, though, is imagine that the same thing is happening as last case. Every step of the way, we've got this slice here, this slice right there, and if we just give it a little bit of thickness, it's now got volume. And if we imagine finding the volume of that coin with a hole in it, and then adding up all the other volumes of the coins, we'll get the volume of the whole shape. So we're going to do the same one-dimensional analysis, one dimension at a time, as we did last time. So first off, let's take the volume of the whole solid. This one's actually pretty easy. The volume of the whole solid has nothing to do with the line y equals x to the 1/2. It is only based on, you can see it over here too, it is the radius of that solid shape is just 3. And so the area of the circle, so we're talking about this circle, but also this circle, and also this circle, all of those circles all have the same radius. It is just pi r squared, which is 9 pi. And so the volume of that slice, using that dv notation that we had from the last video, would be 9 pi times dx. And so the volume of the whole solid would be the sum of all of those disks. Remember, the solid object, like the outer casing basically, is just a cylinder. So it makes total sense that its formula is just 9 pi times height, the area of the base times the height. But if we want to talk about it in terms of integrals, it would be the integral from start to finish of the area of the base times the height. Great. Well, we're going to do the same thing now, but for the holes in the middle. Talk about the hole that we're subtracting. So this time, the volume, the radius of that hole is the distance between, actually I should have drawn it down here, is the distance between the line y equals 3 and the height, and the y value of our curve. So that would be 3 minus x to the 1/2. And so the area, that's the radius, and so the area of our hole would be pi r squared, so pi times 3 minus x to the 1/2 squared. And then the volume of this little hole here, right, has the same thickness as the overall disk. Which is the area of the hole. Put a negative in there that I didn't need to. X to the 3, pi times 3 minus x to the 1/2 squared times the thickness of that hole. And so the volume of all of the holes put together would be the integral from 0 to 9 of pi times 3 minus x to the 1/2 squared in respect to x. And then the key here is that our overall volume is going to be the volume of the entire solid object. If you imagine taking this slice and integrating it all the way start to finish, you would end up with the entire tin can here, cylinder, minus the part in the middle, which is this hole integrated throughout here. All of these slices. So we're going to be subtracting that. And it is the definite integral from 0 to 9 of 9 pi minus pi times 3 minus x to the 1/2 squared, all in respect to x. And I'm not going to worry about integrating that right now, because you'd have to FOIL out the 3 minus x to the 1/2 to do it, and we're not going to worry about that just yet. But coming up with that integral is going to be the key to this lesson.